We're recording? We're recording. All right, cool. Welcome back for another installment of Learning Calculus. So let's get started. Let me see. That's exactly what we wanted. So today we're talking about differentiability. And differentiability means you have the ability to take the derivative of a function. So this says to differentiable, a function must be both continuous and smooth. That's a typo. That should be to be differentiable, a function must be both continuous and smooth. I know some of you are going to be really picky about that because you like things to be right grammatically. So to be differentiable, a function must be both continuous and smooth. Now that sounds like some technical situations, but there are basically 4 different situations in which a function is either not continuous or smooth. One of them is really obvious. If a function is discontinuous, it is going to be non-differentiable. The other 3 situations are if you have a corner, a cusp, or a vertical tangent. And let me just show you some pictures of that. You can also use your graphing calculator to see them. The first one, a corner, is exactly what it sounds like. A corner looks like this. It's just a really sharp turn. And a corner, I hope you guys know exactly what function I'm talking about. It's anything with an absolute value in it. So in this case, this function would be non-differentiable at x equals 0. Non-differentiable at x equals 0. It is differentiable everywhere else, and in fact I can actually see what the derivative is. Just personally, I see I have a negative derivative over here and a positive derivative over here. -1 to the left and +1 to the right. Now looking a little bit further, a cusp is a little bit different. A cusp is similar to a corner, but it's more curved coming in. So a cusp is going to be like x to the 2/3 power. Trying to think of what really breeds the cuspiness to it, and what breeds it is really the squared on top and the cube root at the same time. But just like in the previous problem, this is going to be that's a horrible let me make this a little bit easier to read, non-differentiable at x equals 0. And just like in the previous example, it is differentiable everywhere other than x equals 0. The third category, a vertical tangent. We've seen horizontal tangents where the slope is 0. That's really how we figured out where the graph of the derivative changes from the positive side of the graph to the negative side of the graph. Vertical tangents are going to be like cube root of x, 5th root of x. It's really when we have these odd indices right here. You will see ways later in this book in order to figure out where functions are non-differentiable. As of right now, in general, you want to talk about the picture. So this is going to be non-differentiable at x equals 0. The function is differentiable everywhere else other than 0. And the last one is one that we've already evaluated this type of non-differentiability. It's a discontinuity. Anytime you have any type of discontinuity, whether it's a removable discontinuity, an infinite discontinuity, a finite discontinuity, or an oscillating discontinuity, all of those produce non-differentiability at the point of discontinuity. It is going to be differentiable everywhere else. So in this particular case, that was not a pen that I was using there. So this function is going to be non-differentiable at x equals 0. Right? All of these are non-differentiable at x equals 0. Every single one of these is differentiable everywhere other than 0. So the derivative exists everywhere other than 0. No derivative exists at 0. Like I said, you guys don't exactly have the tools to figure this out algebraically yet. As of right now, you kind of have to go off of the picture, but more on that in just a minute. Now what we have to check for differentiability. Okay, this one's pretty simple. I see my absolute value symbol, right? My absolute value, I know what a graph of an absolute value looks like. my graph of my absolute value is going to look like that. So I know that there's going to be a corner somewhere here. Where the corner exists is going to be more of a little bit of an art form. I remember how absolute values work from Algebra 2. It happens to be the corner is going to be wherever the interior of the absolute value brackets is 0. So when x equals -1, this function is going to be not differentiable or non-differentiable at x equals -1. If you don't remember exactly how absolute value brackets work, I guess you could use your old cheat on this one, and you can see I have this preloaded into y1. If I graph that, yeah, okay, I can see where it is non-differentiable. You just want to give, like when we were talking about continuity, the location of a discontinuity was the x value. In this case, the location of my non-differentiability is going to be the x value on the function, and that's at x equals -1. So I guess as of right now, you might want to go off of the picture, but this activity right here, exploration 1 on page 110, gets at a concept called local linearity. So pause the video, go to page 110, complete this exploration. It has you graph two functions and look at how one is actually differentiable and the other one is not differentiable. So pause it. If you want to do this extension, feel free to do that, and then unpause and come back to me, because really what you should have just done in what I told in when I said go do it was to load F and G into your graphing calculator. I think you were supposed to graph them at different times and look at their graphs. Of course, when we graph them on the standard viewing window, if you've already zoomed in, which you should have because I told you to do the activity, you can hit zoom 6 to get back to the standard viewing window, and they look like exactly the same graph, right? They look like they both have a corner on them. The problem is one of them does not. What you should have looked at, it looks like they both have a corner at x equals 1. What you should have been doing was zooming in, and if you didn't know how to zoom in, you put the cursor where you want to zoom in. So I probably want to zoom in on that, what I think is a corner. I'm going to hit enter. I can see that they start to kind of go apart from each other, diverge, if you will. Look a little bit closer. Look a little bit closer. Keep zooming in. Ooh, look at that. This black one is really going away from the red one. Now keep in mind, when I looked at my y equals, the black one is the one with the square root on it. The red one is the one with the absolute values on it. If I go in here and, whoopsies, zoom in again, I can see they come apart even more. And now I can see that that black function did not actually have a corner. It was just my zoom window was inappropriate for me to be able to see that there was no corner there. Looking a little bit closer. Looking a little bit closer. Looking a little bit closer. Eventually, if you zoom in enough, a function that is differentiable eventually will look like a line. It doesn't have to look like a horizontal line. It just has to look like a line. So the idea here is if you were to use a picture to prove differentiability, you actually have to do all sorts of zooming in on that picture to prove that you have like a corner or a cusp. Now I do see people, or I have seen people in the past get really hung up on the name, whether it's a corner or a cusp. Don't worry about that so much, just as it's not differentiable. Now, just to give you guys a tangible example of this concept, where I'm referring to, sorry, over here. I'm referring to my graph right here. This is called local linearity, where you zoom in close enough to a picture, it flattens out and becomes a line. Now, there is a group of people out there in the world who erroneously think that the Earth is flat. The problem with these people is they can't quite understand calculus. They're standing on the ground, and if you go outside and like you neglect hills and everything, the Earth looks like it is flat. The problem with that is we are so close to the Earth, we're so zoomed in on the Earth, we cannot appreciate the curviness of the Earth. If you've ever been on top of a really tall mountain and looked out at the horizon, you can begin to see that the horizon is a little bit curved. Or if you're fortunate enough to go into a really high altitude spacecraft, you would be able to see the curve. But when we're down here on the ground, the Earth still isn't flat. We're not crazy or anything. We're just not far enough out to see the curve. But yeah, there's a nice example of local linearity in the real world, which is pretty cool. So again, in order to check to see if a function indeed is not differentiability, you need to zoom in to see if the function is locally linear. And local linearity means when you zoom in far enough, it looks like a line. I said move to the next page. Sorry, I wasn't on Active Inspire to advance. So here you can see me zoomed in like 8 times. Of course, I showed you zoomed in like 10 times. On page 111, you will see something called the difference quotient and something called the symmetric difference quotient. Let me pull that up here for you right now. You have the difference quotient and you have the symmetric difference quotient. The difference quotient looks exactly like the limit definition of a derivative. Symmetric difference quotient, pretty similar, except instead of f of a as your second point, you have f of a minus h. If you look at this picture over here, it really shows you the difference between a difference quotient and a symmetric difference quotient. The difference quotient just goes from this point to this point. Symmetric goes out in either direction, so it's more symmetric there. Using the difference quotient, you can actually estimate what a derivative is. And if you look on page 112, we have this right here. Looking at the symmetric difference quotient analytically. And this is just typing stuff into your calculator to estimate what the derivative is. I happen to know that the value of f prime of 10 is 20. You can use your calculator and this difference quotient to estimate, to see what a decent, a close value is. So let's look up here. I've got this blank sheet up here. So if I'm trying to estimate what f prime of 10 is, I happen to know that f prime of 10 is going to be approximately f of 10 plus h. But here, they've actually told us what h is. H is going to be 0.01 minus f of 10 over my h, and again, they're telling us to use 0.01. So in order to evaluate approximately what this derivative is, this is a numerical approximation. I would say, I guess the f we're using here is x squared, right? X squared. So I'm going to do 10 plus 0.01 is 10.01 squared minus 10 squared over 0.01. Now looking at that, I might need to use a calculator. I don't really know what 10.01 squared is. Maybe you do. Maybe you're better than I am. Let's use my calculator and quit out of that. 10.01 squared. Okay, actually here. Let's do this. Alpha 1 equals 10.01 squared minus, I'm going to impress you guys, I know what 10 squared is, over 0.01. Hey, look at that, 20.01. And remember, I told you guys that the actual value of the f prime of 10 is exactly 20. This is pretty close, right? 20.01. The problem is, it's not dead on accurate. I could have made some mistakes in my calculations. This is not the best way to calculate a derivative, but at least it gives us an idea. Now let's look at the symmetric difference quotient now. If I was to do the symmetric difference quotient, so again, I'm going to do f prime of 10 with this particular function. So f prime of 10 is going to be not equal to, approximately equal to f of 10 plus 0.01 minus f of 10 minus 0.01 all over 2 times 0.01. And again, I'm using 0.01 simply because the book tells me to use 0.01. I could go even closer than 0.01. The problem that I have there is if I go to like 0.001, then I have to find out what 10.001 squared is. If I have technology, that's not too bad of a proposition. Now looking at this, this is going to be 10.01 squared minus 9.99 squared over 0.02. I bust out my trusty handy dandy calculator and I can say alpha y equals 10.01 squared minus 9.99 squared over 0.02. Look at that, it's dead on 20. It's probably just a coincidence that it gets it dead on. Usually it's going to be slightly off. In fact, this calculation might be, I'm not sure. There's probably reasons why it's dead on this time. But again, these are always approximations. That's why I'm using the squiggly lines instead of the equal sign there. All right. So estimating your derivative is actually pretty easy to do if you have a calculator available to you. But wait a second. This is so easy, you can actually train your calculator to do it quite easily. And somebody was nice enough to actually train your calculator for you. This function is built into your calculator. So pull up your calculator. You can actually see on the screen behind me, I have the steps for you. There, I'll put it, well, you can't really see it. I'll take away my calculator, pause, write it down. You can actually see it. All right. So now, since you've seen that, I'll just pull up my calculator and run you through the steps on this one. So in order to do this, if you have a TI-84, what you have to do is hit alpha window, and it's right here. It's just end derive. This is if you have a TI-84, you can fill out all of the expressions exactly as you write it down on your paper. You've got d dx of a function at whatever value equals here. So like I could do d dx of x squared. This bar, you guys are going to see it a lot more this chapter. It means evaluate at, and that x automatically is populated to whatever we put as your variable down here. And let's say we wanted to do it at x equals 10, which we just did. Look, it gives me 20 right away. Heck, I could do alpha window, 3 d dx of, find like the hardest function that you can think of. From that assignment that I gave you from last class, 1 over x was pretty difficult. At x equals, let's say at x equals 4. Oh, look at that. Approximately negative 0.0625000039. One thing that I do want to give you guys a caution on, when you have this many zeros there, it's probably not part of the answer. So you can ignore those zeros. The reason why you have so many decimals is because, again, this is an approximation. Your calculator is actually doing the symmetric difference quotient. So anything you get off of your calculator right here is going to be wrong, but it's going to be close enough that you can actually figure it out. Now, I do want to tell you guys there is another way to do this, and if you have a TI-83, you have to do it this way. You would hit Math, and it's under the main Math menu. It's option 8. No, that's not it. I thought I did option 8. Math. I said option 8. I must have gone down one too far. I went to N int. So your calculator on a TI-83 does not look like this. Bear with me, those of you who have TI-84s, you can probably skip ahead like a minute to get past this. I can actually change my calculator to what the TI-83s look like. if you have a TI-83, when you do math 8, it looks like this. And the format for that is actually right up here. In order to do it, you have to do n derive, then do f of x, then comma x, comma whatever number you want to do it at. So if I was doing n derive of x squared, I'd do comma, put your variable there, then comma. If I wanted to do it at 10, I can fill it out that way. It's not as simple, but still, it's a heck of a lot easier than having to type everything into your, like having to type out the difference quotient. And here we had 1 over x, comma, x, comma, 4, just to show you, you get the same value, so your calculator does the same stuff. It just doesn't look as pretty. And just because I'm going to be mad if I don't have this switched back, I'm going to switch back to math print. If you have a TI-84 that you can't do that on, update your operating system, find a way to do that. So here, I think what I have next is to just use your calculator to verify numbers 1 through 9 from the assignment from yesterday. So just emphasizing that sometimes you're slightly off, your calculator's dumb. So another error that you might have is finding f prime of x at x equals 0 if f of x equals absolute value of x. So really what we're trying to do is differentiate absolute value of x at x equals 0. There's what you want to type into your calculator, but I do want to point out that absolute value of x looks like this. And we happen to know that that corner is not locally linear at x equals 0. So that is a corner. This function is non-differentiable. I do want to emphasize that if you were to do that on your calculator, alpha window 3 ddx of alpha window 1, absolute value of x at x equals 0, your calculator is a dummy. And it says that the value of the derivative is 0. The reason is the calculator is doing the symmetric difference quotient. So if I look back at this picture, what your calculator is doing, now this is the wrong thing, it is going slightly to the left, finding that value, going slightly to the right, and finding the slope between those 2 points. So it's really like when we talked in last chapter, the last section of last chapter, when we talked about those secant lines. Your calculator, when it's doing n derive, is not finding the slope of the tangent line. It's finding the slope of a secant line that is a very small distance away from the point of interest, but it's still away from that point of interest. So sometimes you get dumb stuff like this right here. Let's see. Your calculator is stupid, in case I haven't said that enough this year. I try to, but sometimes I forget. Ooh, you know what? You can actually graph a derivative on your calculator. So you can find the graph of a derivative on your calculator. Remember last class, probably I'm doing this well in advance of teaching you this, but I anticipate that that was one of the hardest parts of last class. It usually is. So in order to graph a derivative, let's just graph the derivative of ln of x. To graph something, you gotta go into y equals. Let's clear some of this crap out. I don't need it anymore. So to graph the derivative, in your y equals, you're just going to say n derive. And you're gonna take the numerical derivative d dx of ln of x at x equals, we wanna go at all of the x values. So it's just gonna say x equals x. And when you graph it, oops, I'm still zoomed in. I hope I've shown you guys that hitting on will break your graph, and we can hit zoom 6, and all of a sudden, that's what the graph of the derivative of ln of x looks like. Now just to emphasize that, ln of x, that's not a pen. ln of x looks roughly like that, right? So comparing this graph to its derivative right here, we can see this graph starts off with really steep slope. That's why the derivative starts off really high. As we go to the left on this graph, or to the right on this graph, sorry, it tapers off and becomes more and more flat. It never becomes quite flat because ln always grows. So you can see that the horizontal asymptote of the derivative of ln of x is going to be right at about x equals 0. So like I told you guys last class, you're going to get some more options on how to estimate what the graph of a derivative looks like. You're not going to have the best way to do it yet, but that comes with time. The only way to get better at estimating what the graph of a derivative looks like is by practice, practice, practice. All right. This theorem has a really dumb name. It's called differentiability implies continuity. If f has a derivative at x equals a, then f is continuous at x equals a. What? Why is that? Well, because if a function is not continuous, then it is discontinuous. And if a function is discontinuous, it is non-differentiable. See the 4 cases from earlier today. So in order for a function to have a derivative, it has to be continuous. So if it has a derivative, then it is continuous. And I've seen this theorem pop up on the AP test. Like they will just say a function is differentiable, and you have to take that to mean that it is also continuous. Intermediate value theorem for derivatives, similar to the intermediate value theorem from last chapter, but now it's more particularly about derivatives. If a and b are any points in an interval on which f is differentiable, then f prime takes on every value between f prime of a and f prime of b. And basically what that means is, if I'm sitting in my driveway, all right, and the velocity of my car, velocity you'll learn in a couple of sections, is itself a derivative. So if the velocity of my car is, let's say, 0 when I'm sitting in my driveway, and then I get up on the highway and I know my velocity is 70 because that's the speed limit. I never break the speed limit. So at some point between when I was in my driveway and when I was on the highway, was I going 30 miles an hour? Yes, at some point I was going 30 miles an hour because that's between 0 miles an hour and 70 miles an hour. Was I ever going 100 miles an hour? I don't know. Maybe. Probably not, because I just said that I don't break the speed limit, but I could have. I could have gone higher than the highest speed limit. Could I have been going -5 miles an hour? Maybe, if I pull in headfirst in my driveway and I needed to back out. But again, what the intermediate value theorem for derivatives says, if a function is differentiable on an interval, and a and b are on those intervals, or are the endpoints of that interval, then f prime takes on every value between f prime of a and f prime of b. And I believe that's it. We're going to go over these tomorrow in class. I feel like this was a really short lesson. Hope you liked it, but I will see you guys tomorrow. Goodbye.